heat and the second law of thermodynamics. Thermodynamics began as an application and extension of the basic idea of energy and energy conservation. The thermodynamics really started off by arguing that thermal energy is just another form of energy. We don't need to hypothesize some mysterious new substance. We can just think about the flow of energy in order to understand the object warming up and cooling down. The first law of the thermodynamics is just a mathematical statement of conservation of the energy. There are many applications of this idea, and the most significant that I can think of there in our lives would be something called a heat engine. Heat engine is a generic term. It's a device that drove the industrial revolution. It's what powers our homes. It's what runs our cars. A heat engine is a device that converts thermal energy from the one place, move it, and does something with that energy. That is really the idea of a heat engine, and this is what we want to talk about today. In order to talk about it, we are going to have to introduce a new concept, the concept of entropy. But let's just begin by thinking about broad properties of heat engines. They are made of many different kinds of designs. I can think of lots of the different kinds of the heat engines. You always have a hot bath. There is some place that is hot in your automobile. You are burning gasoline and you have a little hot spot. There is always a cold spot. We call it a reservoir, and this cold reservoir is the exhaust. In your automobile engine, the cold spot would probably be the outside world that is at a cool temperature. Then there will be some working material, and the idea of the heat engine would be that the working material, it might be a gas or liquid, as there are all sorts of different kinds of design, is going to take some of the thermal energy from the hot stuff and do something. If what you do is convert that thermal energy into work, that is to say, into the mechanical energy, I should really use into the work. That is to say, into the mechanical energy, I should really use the proper word. If you convert the thermal energy of the fuel or the hot spot into the mechanical energy, kinetic energy, that would be like an automobile engine taking the hot gases, driving pistons and moving the car. You are moving energy from the thermal place into the kinetic energy, a different form. You could, in principle, move the thermal energy from a hot place to a cold place, or from the cold place to a hot place. Those would also be heat engines. When we are thinking about air conditioning your house or running your refrigerator, all you are doing really is moving thermal energy around. Moving thermal energy around, you are taking it out of the water, turning the water into the ice cubes, and dumping that thermal energy into your kitchen. That is another kind of the heat engine. In order to understand heat engines, remember that in the old days, people were just building these things and they didn't really understand them. 200 years ago, people were designing steam engines, and there wasn't a good, rigorous physics underpinning for them. They were tinkering, there were some engineers, there were some principles that were being developed, and people began to build steam engines. By 1800, you could heat up water and then use that hot reservoir of water to drive a piston. That's a working fluid, and that pushes the wheels through some crank systems. You could convert the thermal energy into energy of motion, and people were becoming more and more frustrated because they knew that they were putting in a lot of energy. They were burning a lot of coal, and yet they weren't putting out of the whole of lots of energy. They were not climbing big hills. They were not going very fast, so there was a poor efficiency. There was a lovely point in the history of the science where the tinkering, engineering, and physics all began to work together so that there was this practical drive for the physics. The theory and development of the law of the thermodynamics were fueled and became immediately useful for people to understand how to apply this stuff. It's a lovely interplay. It's a lovely interplay which continue to this day. I think it's a part of what it means to be doing certainly a classical physics and maybe any kind of physics. The question that is coming to the forefront with these steam engines is efficiency. We are going to define efficiency gravely as what you have divided by what you paid for. So it's like it is all about ROI, return on investment, right? For an engine, what you have means how much mechanical energy the device provides you, how high up does the object go, or how fast does it go. That's a useful energy. That's a numerator. That's a and the denominator is how much energy you put in. So yeah, return on investment. So investment is denominator. Return is a numerator, right? So how high up does the object go, or how fast does it go? That's a useful energy. That's a numerator. The denominator is how much energy you put in, measured as the chemical potential energy of the coal, or the gasoline, or whatever source of energy you started with. Think about conservation of energy. What you have can never be greater than what you put in. What you take out can't be greater than what you put in, because that would be the obvious violation of the first law of thermodynamics. The first law says efficiency. What you have divided by what you paid for. Again. The first law says efficiency. What you have divided by what you paid for will always be equal to 1, or more likely in a practical situation, less than 1, because you can always throw away some of that energy, right? Imagine if you are burning a coal and it's not really doing a whole lot. It's just heating up the atmosphere. That's not useful energy for a steam engine. Now, it might be useful energy if you are warming up your house. So the efficiency might be different depending on the purpose. But if you are thinking in particular about heat engines as real engines, they can see that practical engines could be much less efficient than 1 or 100%. If you start off with a small amount of gasoline that has 1,000 joules of stored chemical potential energy in it, it is well defined. You have a certain amount of gasoline, you know how much energy there is, and you know in the principle how much work you could take out of it. In practice, when you burn it in a real-life automobile, you won't take anywhere near that 1,000 joules out again in the form of the kinetic energy of the car. You might, if you have a really efficient car, a couple of hundred joules. So if you have a joules of useful work and you put in the 1,000 joules in the form of the low chemical potential energy, the efficiency of that engine is 200 divided by 1,000. That's 20%, and that means that 800 joules by conservation of energy by the first law of the thermodynamics must have been thrown away. Wow, such an inefficient. Now it doesn't disappear from the universe. Where does it go? It warms up the cold reservoir, which in this case is the atmosphere. Wow. So this is pretty much about equivalency, like a buffer, phosphate buffer, in the physiological condition of the human body or any animal or plants, right? Because the cold reservoir is so big, 800 joules of energy isn't very much spread out over the countless billions of atoms. They don't have to change their temperature very much and maybe even not noticeably, and yet you still have a conservation of energy. conservation of the energy has put a limit of 100%, and back in the early 1800s, people were looking at 1% of the engines at best. They were really struggling to be efficient. There is a new law of physics, the law that we want to talk about today, in which we discover that you cannot even approach 100%. It's much worse than you might have thought. The second law of thermodynamics gives us a mathematical formula that tells us what the maximum efficiency is of the perfect, ideal heat engine. This was discovered originally by Sadi Carnot. He was a French engineer, and he was very interested in the steam engines. He also did some good physics, and part of the brilliance of the Carnot back in the 1800s was his ability to look at all of these different steam engine designs and step back from the details. Okay. Never mind that fluid they use, never mind what fuel they use, never mind the mechanical design of the pistons. Just think about the broad principles, the law of nature that are involved, and what he recognized was so simple that you may not even be able to imagine how this could put a quantitative limit on efficiency. What Carnot recognized was that all of the engines work in the same fundamental way. There is a thermal energy in a hot reservoir, and you take that energy and do something of it. You do some useful work and turn that into a kinetic energy, and you also threw away some of it. You always threw some of it away into the cold bath, into the cold reservoir. What Carnot recognized was the physical underlying principle of any design, and what always happened in nature, is that warm things spontaneously cool off and cold things spontaneously warm up when they are brought together but isolated from the rest of the world. Wow. It's a law of nature. It's a second law of thermodynamics that if you have an isolated system and the one part of it is hot and the other part is cold, the hot part will cool while the cool part warms up until you reach equilibrium. Now think about for a second. It's a new law of nature. It may be obvious. It's obvious from our experience, but it is useful to recognize the fundamental nature of obvious things. Why couldn't it happen that you have two pieces of the object, maybe two buckets of the water, and maybe one of them is a little cooler than the other, and the cold one just becomes a colder still, and warm one just becomes warmer still? Because of their spontaneous contact with one another, why couldn't you have the cold grow colder and hot grow hotter? It could still conserve energy if the total energy of the cold one decreases and the total thermal energy of the hot one increases. You could have the amount of balance and preserved. The first law of the thermodynamics? Yes. The fact that it doesn't happen is the second law. Wow. Carnot recognized this, and his brilliance was that he recognized there were many concrete consequences of this. One of the consequences was that if you run the heat engine and you have a certain temperature of the hot bath, you have the certain temperature of the cold bath. You will be limited as to what fraction of the thermal energy stored in that hot bath that you can let out. What is maximum possible efficiency? Carnot used the logic and the mathematics and argued that the maximum depends only on the temperatures. Maximum depends only on the temperatures. That's the best efficiency you could ever come up with. You are talking about the perfect design, no friction, no internal problems, no poor design, and even in this ideal case, the maximum possible efficiency will be limited. It's a simple formula. The efficiency basically depends on the ratio of the cold temperature to the hot temperature. If you start off with boiling water, that's a steam engine and the boiling water is at 100 degrees Celsius and it's running some sort of cycle. You are pushing on the pistons because they are hot now and they are expanding gases and they are pushing on iron rods and then you have to cool the gas back down again in order to repeat the cycle. You have to always have a cycle if you want the engine to keep running, and that's a part of Carnot's insights. Wow. So if you look at the temperature involved and you look at the Carnot's formula, which I haven't derived for you, but I'm just stating, the maximum possible efficiency is very depressing. For steam, 25% for every useful joule, you throw away another 3. That seems very painful, and at first the engineer working on the steam engine said, "Oh, I realize that right now we are only at 2%, but we are not shooting for 25%, we are shooting for 100%, or let's be realistic, 99.99%. Yes. They weren't being realistic because they didn't recognize that Carnot rule is not an approximation. It's another one of those fundamental laws of classical physics. In the end, if you think about world being made of atoms, and we talked a little bit about this, the statistical, mechanical view of the thermodynamics story makes the story even more rigorous. It's really a law of nature that arises from counting how atoms rearrange themselves and how they are moving, and there is no way around it. What? This is not a law of physics that you can struggle from there underneath any more than the conservation of energy. It's a statement about how the world works, and so not only should you not buy a free energy machine that doesn't take any fuel but produce some sort of the output, but you shouldn't even invest in a machine that has 90% efficiency by burning something, because if it's a burning something, it is a heat engine. If it's a heat engine, you can't possibly have 90% efficiency. Mr. Carnot's formula tells you that to do so, your hot temperature would have to be so hot that ordinary objects would vaporize. So you couldn't make it in any practical sense. Yes, you can increase the efficiency of engines, but to do so, you have to make the temperature difference much and bigger than you normally would in ordinary working circumstances. Wow, that is why this is not realistic, right? Seeking for high efficiency just by considering their heat engine. That is why in the Formula 1 car they brought the electricity to make engine more efficient, because this is not only a heat engine but also it is electricity. The loss of the heat is stored in a way of the electricity, converted into the electricity in the battery. So that is why you have just 6 pistons and the powerful batteries. That is why the latest car in the F1 is the fastest, quickest in the history. The second law of thermodynamics can be thought of and stated in many different ways. It's one of the pleasure of studying thermodynamics as a career to begin with, to begin to realize how all of these different ways of thinking about the second law all hook together. Some of them seem intimately related, and some of them seem really different. The one I'm about to tell you is a new concept. It's a way of reframing the same second law of thermodynamics. It's a concept of entropy. Entropy is a number. You can measure it. If you have a pot of water, it has an entropy, and you can measure the energy. Now, energy, of course, is also a fairly abstract concept. How would you measure the energy? You'd need to really have some deeper understanding of what's going on and what energy means. Energy tells you how much work you can do. So energy tells you how much work, which is force times distance, right? Joule, right? How much work, how much energy you can do. So measuring energy is a tricky business. Measuring entropy is even trickier business. Now, what is entropy measuring? In the early days, in the post-Carnot days, people were beginning to recognize that there is this number. It is associated with system and it changes. As you do things, you can increase the entropy or you might decrease the entropy. People came up with the thermodynamics rule for measuring how much the entropy changed over time. Wow. Ultimately, the statistical, mechanical worldview taught us a way of thinking about entropy microscopically. It's a measure of the randomness. It's a measure of randomness. It's a measure of order. It's a measure of the order. The more orderly something is, the less random it is, the less entropy it has, and the more random something is, the more entropy it has. It's a quantitative measure of the randomness. What do I mean by randomness? Well, microscopically, I mean counting how many different states are available. States would be different configurations. One way that you could give a pot of water more available states would be to warm it up, because now the molecules are jiggling around faster, so they have more opportunities in their life. They can go a little bit faster or slower. There are more options for them. And of course, you think about them jiggling around more, and so this idea of randomness is nice and deeply intuitive. Adding energy is one way of increasing the entropy, but it's not the only way. Energy is not the same as entropy.